Hello everybody and welcome back to Python for Aerospace. In today's lesson we are going to learn how to compare the aerodynamic coefficients calculated in the previous lesson to experimental data which is contained into this technical report created by NASA, which is available in the Jupyter notebook that I linked in GitHub. The experimental data is contained into a PDF like this one. And as you can see, it's not in machine readable format. So what we're going to do is to sample with Python all the points that form all these curves. Then we're going to set the correct range for each axis. And then we're going to plot the captured values with the ones calculated in the previous lesson. So I hope you guys ready, and let's get started.
It's one small step for man, one giant leap for mankind.
So the first thing we need to do is to find, after downloading the PDF, is to find the correct data that we want to sample. In our case, we want to find the NACA Airfoil 4418, which is the one that we have calculated the aerodynamics coefficients with Airfoil, and let's look for it. And as you can see, we are here on this page 143, and we found the following curves. Now, as you can imagine, there is not just one curve for each aerodynamic coefficient, but they also depend on the Reynolds number. As a matter of fact, if we check here at the bottom, we can see that different type of points have been used to represent each different configuration at a different Reynolds number. So we can see that squares represent the 600,000 Reynolds number, which is the one that we are interested in. Therefore, if we want to sample the values for the lift coefficient, which is this curve here, we want to capture the point, the square, the square symbols of the curve. Oops, yeah. So this one, this one, this one, this one, and so on. Good. So how do we do that? The first thing we need to do is to get a snapshot of the graph. We can do this by using, for example, snipping tool that you have installed in Windows. If you are in Windows machine, if you are in Ubuntu, then I believe you have to use some other tool to do that. But anyways, and here we gotta be very, very precise. Okay, like so. We start at the corner and we end up at the very bottom right corner. That's it. So let's save the image, and we can save it somewhere in our computer. In my case, I have already saved it, so I don't have to do that. Okay? Good. So once you saved it, you will probably have something like this. Okay? That's your image. So let's start by importing this image into Python. So in order to do that, we need first to import the following library. So import CV2. Good. Once we have CV2, we can read the image, right? So let's do that. Actually, yeah, let's do here. Read image, and here we're gonna have image equals to CV2 dot im read, and here we're gonna have the path to the image. So in this case, I like to use OS library in order to join the path with the file name. So how is it? it's os.path.join, and inside we're going to have the relative path to the folder where the images are stored in my project, and the file name is going to be this one for me. Okay, so let's launch the cell, and it looks like there are no mistakes. Let's print the content of image. Yes, and we can see it's like an array of arrays, or no, it's a list of lists to be correct, where we have the pixel values of the image we captured before. Good. Let's try to plot the image and see what it looks like. So plot the image with CV2. And to do that, it's easy. We can call CV2 and the method imShow, and inside we can give a name to this plot image, and we're going to call the object image, or yeah, which contains the pixel values. And we can see we have a mistake here because it's actually CV2. Let's do it correct. Good. And we can see that Python has opened something, and it returns error. As we can see, the image is like all grayed out, so it doesn't really make sense. So how do we solve this problem? Well, it's pretty easy. Well, if you close it, actually it will make the kernel fail. So we have to restart it, unfortunately. So let's do that. So after we have restarted the kernel, what we need to do is just to add the following line of code, which is called CV2 wait key 0. Okay, this method will allow us to keep the image open, okay, and visible without any crash. So let's do that. Oops, here again it's CV2, and we have the image finally as we want, and we can close it and no problem. And to close it, we can actually add another line here, and it's gonna be CV2 destroy window, and we pass the image name. So that's the proper way to close the image. So we can add some comment, for example, close image. Perfect. So the next step now is to have a function, okay, that will allow us to capture all the pixel coordinates every time we click it with the mouse on the curve. Okay, so let's do that. And oops, here we need to fix again this error, CV2. So let's define the function, and we're gonna call it def, and we call it mouse points. This function will capture the coordinates of the points that we click on the image. So here we need to have an event, and we need x, y coordinates, then we can have flag and parameters. Okay, now, not all of the inputs are necessary, but this is how it usually works. So that's right, if event, okay, is equal to cv2 dot event, and here we have left L, capital L, button, down. So every time we click with the left button of the mouse, what happens? Colon. We need to capture the coordinates, right? And we're gonna store it into a list. So we're gonna have something like this: x coordinate dot append x. So every time we click, we append the value to this list, which we need to define. like this. And analogously, we need to do the same for the y coordinates. Like that. Oops. Yes, square brackets. So y coord dot append, and here we have y. Now we could actually print the values, and to do that it's very easy. We can do print and then a string, right? Where we have the xy coordinates. And I think this is helpful to understand how the pixels are ordered in the image. So let's have format and then x and y. Okay, so let's launch the code. Yes, no mistakes so far. Good. Now what we need to do is to call this function, right? We need to call it so that we will be able to capture the values. So let's do that. So after where we have opened the image, we can write get mouse coordinates from image, and here we're going to have cv2 dot set capital M mouse capital C callback, and then we have image, the image name that we defined previously, and then we're gonna call the method mouse points. Good. Let's launch the code, and we can see that the image is open correctly. And let's check if we click the coordinates, the xy coordinates. And yes, you can see at the bottom of the cell, coordinates are open. Now, this is an important step because we need to see how these coordinates are referenced. So usually coordinate 0, 0 for us would be at the bottom left corner, right? But if we click here, let's see what happens. No, we don't get 0, 0. We get 2, okay, which is almost 0, but then we get 692. So it looks like the x coordinate is making sense according to the logic. So we have 0 here, and it's incrementing going towards the right, but the y coordinate is not. So let's see. If I click here, the y coordinate starts to become 0, basically. You see? Here it's 1. And if we go down, it increments. But we would like to have the opposite, right? We would like to have that the y is about 0 here, is actually 0 here, and increments going up. So how do we do that? This is simple, or not so simple actually. It took me a while to figure out, even though afterwards it makes sense. So every time we capture the y coordinate, we need first to make it negative. So, and then we have to translate it, okay, by the amount of pixels in the y direction. And how is that possible? Well, we're going to use parameter here. Pass a parameter that flips basically the y coordinates, and this can be done here, defining the variable parameters, which is equals to the image shape basically. And as a matter of fact, if we do print image shape, yeah, we see these 3 numbers, and this is the y coordinate basically. And we need to add it to the negative y variables. So parameter will be passed as an input of the method, like so. And here we're going to have parameter 0. We access the first item. So let's do the same for the print here. So copy and paste here. And now let's test it and see if it actually works correctly. So Control Shift and then let's try to click, for example, down here. Yeah, now we can see that the X and Y coordinates at the bottom left corner are basically, well, 0. So it means that we have implemented the correct algorithm. Very good. So the last thing we need to do is to store the capture data into a file that then we can use to manipulate and to transform the XY coordinates from pixels to actual units that can be compared to the calculated data from Airfoil. So let's save the data in the following way. Save data. We're gonna open a file. Open file. We're gonna use the OS library again to join the relative path data to the file, which in this case I'm going to call CL 4418 600,000.txt, and this file is going to be open in the write mode. Then we're going to have a for loop to loop through all the captured x and y's. So we can do that defining x and y, and we're going to iterate in a list which is given by putting side by side the x and the y coordinate. So we need to use a zip which puts x coordinate and y coordinate side by side. So then we're going to write the pair x and y into the same row. So we need to use f, write what? We need a string here where we have the x and y's in the same row, and for each iteration we go to a new row. So then we have format and here are the x and the y. Good. Finally, we can close the file like this. Let's launch it and test it. So again, let's capture all the points of the curve. You need to be quite precise. I'm not going to be too fast, but doesn't matter for this demonstration. So we capture the points and let's check if the file has been saved correctly. So we can see that the file is right here. If we open it, we can see also all the points as expected. Very good. So what we can do now is to convert the data from pixels to the units that we need to compare the captured data with the one calculated from Airfoil. So let's do that. Convert data to correct units. Okay. In order to do that, we need to know the range of the x and y coordinates, and we can find out that in our PDF. For example, the x coordinate goes from -32 to +32 degrees. On the other hand, the y coordinate, which is the lift coefficient, goes from -2.0 to 3.6. Okay. So we're going to use this to create a linear interpolation, which allows us to convert pixels to the degrees and a dimensional lift coefficient. So we can define, for example, the x range, which is equal to, it's a list and has two values, -32 +32, and the y range is again a list that goes from -2 to +3.6, as we just saw. Okay, so we can have the equation of the line. We can use the equation of a line in order to transform the pixels into the same range as the experimental data. So we can do the x of the experimental data is going to be to the x range, and we're going to have the first item minus 32 plus what? Then we're going to have the following ratio: x minus range, x range, sorry, and we're going to have the first item minus the x range and the first item, so basically 32 minus 32, so 64, and we're going to divide this by the number of pixels along the x-axis. So image shape, shape 1, not 0, it's 1. Okay, and then we're going to multiply this by what? By the x coordinates, right? And we need to convert them into an array. Let me check my notes, but it should be here. An array, and here we have x coordinates, right? Yeah. Let's check if this is working correctly. Again. Yeah, no, we don't have NumPy. We need to import it. Or, yeah, let's import the NumPy. NumPy as NP. Great. And I think now it should be working correctly. And let's copy this, and let's do also for the y coordinate. So, oops. So y range, and so on. Here we're gonna have 0 and y. Okay. Let's give it a try. I'm gonna use just a few points. I don't need to use them all for the moment. Yes. And let's check the values of x. Yes, they are converted. And if you don't understand this, well, actually, let's make a simple experiment. If the x coordinate, so the pixel, is 0, then we are at the bottom left corner of the graph, and this is equal to minus 32, which is actually the item 0 of the x range. And same thing is for the y coordinate. If the y coordinate is 0, then we should have minus 2. And that's true, right? Because if this is 0, multiplies all these numbers is 0, and here we have minus 2. Very good. So we can move on now, and we could have a function that runs all of these lines of code, and it will capture the values from the image only if the file doesn't exist. If the file already exists, we don't need to recapture them, right? And it will skip all this part where we click with the mouse on the image, and it will just convert the pixels into the values that we are looking for. So let's do that. We can create the function up here, for example, and we're gonna call it def sample experimental data, and it's gonna take as an input what? I would say a file name, then the image, then the x range, the y range, and what else do we need? I would say, yeah, that's enough. Now, most of the code for this function is already here, so that's indented. Okay, and in any case, we would like to have the image open, right? And then we can check if the file it exists, the file exists. So os path dot is file to check if the file exists, and here we're going to have os dot path dot join, and we're going to have what the relative path to data and the file name. Okay, and what else? I think we're good. So let's check if the file exists. Then what? Then we can read the file, okay, and extract the data. So that should be quite easy. We can open the file in the read mode. So os.path.join. Here again the relative path to where I store the data, and here the file name. And it's gonna be again, as I just said, read mode. Okay. Then we can have another variable where we're going to store the content of the file. So content is equal to f.read. And we need to notice that content is a string, okay? So now we want to iterate through each row of the content. So in order to do that, we need to do for row in content. And since this is a string, we need to split it every time we have a new line. Oops, like this. Okay, and we need to remove the very last line because it will not contain any, it will be empty line, so we need to remove it. So here is how you skip the last line. Nice. And finally, we would like to store the XY coordinate. Like so. So append an integer, which is given by row, and we need to split it at the comma that we defined down here, this comma. So split comma, and the x is the first value, right, of the list, and same for the y. Okay, so here y, and here's gonna be the second value. Very good. Once we are done storing all the items, we can close the file, right? And yeah, here it's path. So let's save it. If the file doesn't exist, then else, what we're gonna have is this. So save or sample experimental data, and that's where we're gonna open the image and save the quantities as we did before. So like so, and the only difference here is the file name. Okay, file name, which needs to be defined, and it's an input of the function. Finally, we can do what? We don't need this because it's an input, and we can return the x and the y. So the experimental data. And I think at this point we're good. The function is here, and let's test it in the case when the file doesn't exist and when the file exists. Okay, so let's remove it from here. Okay. Okay, it doesn't work at the moment, but let's rename it in a different way. CL 4418 600,000 new txt. Okay, so this file doesn't exist. Then the image name is this one. So we need to modify here and have image and copy paste the image name here. Okay, and also we need to be careful here. This line of code needs to be just inside of this else statement. Okay, all right. And finally, we need the ranges, the x range, which goes from -32 to +32, and the y range goes from -2 to 3.6. Okay, so we can run the function and let's see if it works now. Yeah, in this case, the file already exists, right? So let's modify it a bit, and let's rename it, I don't know, underscore here. Yeah, if it doesn't exist, then we can select the points of the function, right? Like so. And we can see also that a new file has been created into data. Right? Yeah, right here. And these are the points that we just sampled. So it looks like the function is working correctly. So successful so far. What we would like to do now could be to display the experimental data, right? So the x and y need to be renamed. We can say the x is actually alpha experimental and the y becomes CL experimental data. Okay, and now we can define import matplotlib. So let me get it from my previous lessons here. Okay, so let's import matplotlib, and we have plt figure, and here fig size, equals to 12.9. Then we're gonna have plt plot alpha experimental versus CL experimental. Then we're gonna have everything in blue, and we're gonna label it as CL lift coefficient, and then we're gonna do plot GCA dot legend, okay, to show the legend. Then we're gonna have plot X label, and here we can write alpha space, and here degrees, okay, and plot y label, and it's CL no units because it's just a number, and the title plot title, which is CL over alpha, and alpha is given by U0 3 capital B1, here capital B1, and it's NACA experimental. And here we have format what? NACA series, right? Or in this case would be NACA 4418. 18, yeah, as a string. And last row is plot show. There is a mistake in the title. Let's see why. Yeah, this one. boom, we have our experimental data. So mission almost accomplished. What we're left to do is to compare the calculated data with the experimental one. But this is very easy task, as we just need to call, again, these lines of code and an extra one from the previous lesson, and then we are basically done. So let's do that. So let's start by copying all these lines here, right? And then we're gonna have to modify a bit this row. Okay, so we're gonna change the color into red, and then we need the following lines of code, where we call the NACA object we defined in the previous lesson, where the Reynolds number is 600,000, okay, because we need to compare with the experimental data for the configuration at 600,000. And then we also can use the implicit case where there was no viscosity. All right. Finally, we can change the title like so. And let's run the code. Okay. We have some mistake. Let's check why. Oh yeah, the mistake is right here. Is the degrees go from -20 to +20 in my case. And let's test it now. Yes, good. So we can see that low angles of attack, the three curves are more or less similar. They have the same slope, and this is because the viscous effects are not yet present. But as we approach the stall and the separation of the flow from the surface of the airfoil, yeah, we can see how the experimental data and the one calculated by Xfoil more or less follow the same shape, but there is some great difference with the implicit case, which is actually just an approximation which works well when we have low angles of attack. Okay guys, this is it for this video series. I hope you enjoyed it and learned something. If you have any questions, please write it down in the comment section below, and I will try to reply and help you out. And always you can download all these codes from GitHub and do whatever you want with it. And I hope to see you in the next video tutorial series that I will create. And if you like it, leave a thumbs up and subscribe. Bye, and thanks again.